Good day. Today I'm going to explain what is shock waves and supersonic wave formation. But first, what is supersonic speed? Let's consider this moving object. If this object moving slower than the speed of sound, then this object is moving in subsonic speed. But when this object increase in moving and move faster than speed of sound, then this object is moving at supersonic speed. Let's see what change happen when the aircraft starts flying in supersonic speed. Then consider this is an airfoil sa subsonic speed. Bab o kaya mga babae tas yung hangin tayo mga lalaki. So yung airfoil flying at subsonic speed, yung air particles sa unahan or sa airfoil natin o sa ating leading edge, tayo yung mag-a-adjust kasi palagi naman tayo mga lalaki yung nag-a-adjust. So, pero sa supersonic speed, kasi mabilis magalit yung mga babae, wala tayong time para makapag-adjust. So, yung hangin sa unahan may ipon. Then, magpo-form siya ng tinatawag natin na shock waves. And kailan nga ba napo-form ang shock waves? As the object accelerate from subsonic to supersonic speed, yung shock rip na tinatawag natin, nagpo-form siya sa ating airfoil. Yung airspeed sa taas ng airfoil natin is mas tumataas kaysa dun sa actual speed. So, sa taas ng airfoil natin, ma-reach niya ngayon yung tinatawag nating supersonic speed, then mapo-form din yung shock wave. May impact din yung sa ating aircraft kasi yung effects ng subject sa aircraft natin is nag-i-increase siya sa drag para ma-overcome yung gantong mga pangyayari. Need ng aircraft natin ng more thrust. Then there are two types of shock waves, normal shock waves and oblique shock waves. Yung normal shock waves na-perform siya perpendicular to the airflow at yung oblique naman pa-angle sa airflow.
The next topic is all about boundary layer, types of boundary layer and impacts of a boundary layer.
A boundary layer is a thin fluid layer which is formed on the surface of an object. Boundary layer is created due to friction between the fluid and the moving surface. Air is a viscous fluid. This means when an object such as an aircraft moves across the air, there will be friction between the surface of the aircraft and the air. Because of this friction, the air particles which are just above the surface will stick to the surface. When this particle is compared to a particle further away from the surface, the speed of the particles will be different. The speed of the air particle that is further away from the surface is the free stream velocity, and the speed of the particle that is sticking to the surface is zero. As we move higher from the surface, the speed of the air particles will increase gradually until it reaches the free stream air velocity. The region in which the speed of the air particles varies from zero to the free stream velocity is called the boundary layer. This boundary layer will form only in a viscous fluid. There are two types of boundary layers, laminar boundary layer and turbulent boundary layer. A laminar boundary layer is one in which all the streamlines in the boundary layers moves parallel to each other. A turbulent boundary layer is one in which the streamlines are not parallel and the particles tend to move randomly within this layer. A laminar boundary layer reduces the skin friction drag. The wings of an aircraft try to maintain a laminar boundary layer to improve the aerodynamic efficiency of the wing. A turbulent boundary layer is thicker and causes more skin friction drag, but a turbulent boundary layer carries more energy. This means it can withstand an adverse pressure gradient longer than a laminar boundary layer. An adverse pressure gradient disrupts the flow across a wing or any body moving across a fluid. An adverse pressure gradient is a sudden change from positive pressure to negative pressure. This will result in flow separation over the surface and consequently an increase in the pressure drag. A turbulent boundary layer will oppose the adverse pressure gradient and prevents the flow from separating over the surface. A turbulent boundary layer may be forcefully induced on a surface in order to prevent the flow from separating and thus reduce the drag. Let us look for a few examples. On some wings, there are vortex generators installed on the top surface. These vortex generators will create a turbulent boundary layer and prevent flow separation over the wing. Other examples are dimples on golf balls and rough surface of tennis balls. The dimples and the rough surface will induce a turbulent boundary layer and reduce the drag force.
I will read and discuss about the mechanism of drag. There are two concepts of drag of a body moving in a fluid medium. First, one may consider the pressure and friction forces acting on the surface of the body and determine the resultant. Second, one may consider the body and a sustainability bounded region of the surrounding air as one mechanical system and compute or measure the normal and tangential stresses acting on the boundaries of the system, called control surfaces, plus the flow of momentum due to the fluid entering or leaving the system through the same boundaries. The engineer may look at the first concept as a more direct one. Often, the second concept is more practical. However, shown, for example, by its successful application as an experimental method, it is commonly known that the best determination of the profile drag of an airfoil section is achieved by the so-called wake method, which is precisely an application of the second concept. Also, in the age of propulsion by reaction, every engineer should be acquainted with the definition of forces acting on a body by action and reaction. So, according to the so-called paradox of D'Alembert, the motion of body in a non-viscous, incompressible fluid does not involve drag if the motion does not produce eddies and the flow does not separate from the body. This statement is based on the existence of a vertex-free motion around the body, in which all disturbances completely disappear at infinity. The resistance in the actual fluid is then due to a friction forces and fluid separation. The loss of momentum equivalent to drag can be found in the wake that follows the body. This statement concerning the relation between wake and drag is also correct for the motion of the body in a compressible fluid if the motion is subsonic. Moreover, the drag is zero. The D'Alembert theorem holds a non-viscous compressible fluid provided a vortex-free continuous motion around the body, whereas, however, in the case of an incompressible fluid, the equation of the flow allows admits such as a solution. In the case of a compressible fluid, this is true only below a certain critical Mach number that is less than unity. Between this Mach number and Mach number 1, the wake is due not only to friction and flow separation but, as will be shown in a later section, also to the existence of shock waves. Hence, although the mechanism of the wake formation may be more complex in this case, nevertheless, the total loss of momentum equivalent to drag always appears in the wake as long as the body moves subsonic velocity. If the body moves at supersonic velocity, a new type of drag appears. For convenience, consider the air non-viscous and assume that the motion of body produces disturbance that can be considered small. at a certain distance from the moving body, this second consumption will in general be satisfied. Consider now the body and the surrounding air inside a cylindrical control surface as one mechanical system. Then one finds that because of the concentrated action that characterizes the pressure propagation from a source moving at supersonic velocity, the total flux of momentum of the air masses entering and leaving the cylindrical boundary remains finite even the boundary is removed at an arbitrarily large distance.
So, to continue the discussion on basic supersonic aerodynamics, here's the mechanism of the lift. So, what is the mechanism of the lift? The theory of lift of an airplane when moving at subsonic velocities is based on the concept of circulation. The origin of the circulation can be described in the following way. Consider an airplane wing initially at rest and suddenly given a forward velocity. The equation of motion admits a solution that represents a flow without circulation and therefore without lift. However, this flow has infinite velocity around the sharp trailing edge of the airfoil section. Since some viscosity always exists, the following separates with consequent formation of a vortex, called the starting vortex. The reaction to the starting vortex produces circulation around the airfoil. The final magnitude of the circulation is determined by the condition of smooth flow at the trailing edge, called the Kutajukosi condition. The condition of smooth flow is equivalent to the statement that the lift per unit area is zero at the trailing edge. The pressures acting on the edge at the upper and lower surface of the airfoil are equal. It is easily seen that this process is in general impossible in the case of supersonic motion. Consider, for example, the two-dimensional case, the case of an airplane wing of infinite span, the trailing edge being normal to the flow direction. It is evident that according to the rule of forbidden signals, no process at the trailing edge can have an effect upstream. Correspondingly, the lift density at the trailing edge may well have a finite value. This is also from Accurat's rule that the pressure produced at every element of the surface depends on the local angle of attack. It is seen that the lift distribution near the leading edge is also different in both cases. In the subsonic case, the theory gives infinite lift density for a plate with mathematically sharp leading edge. This is consistent with the fact that the air is supposed to flow around the leading edge with infinite velocity. One might object to the inconsistency that the theory admits infinite velocity at the leading edge and forbids the same of the trailing edge. The reason is that although the fluid separates at the sharp leading edge, it will again become attached to the upper surface at least below the stalling angle. In the case of suitably rounded leading edge, the flow will follow the surface continuously. The flow around the edge produces negative pressure, which is simplified theory of the flat plate or infinite thin wing is taken into account by the assumption of concentrated force at the nose. In the supersonic case, it is possible to build up a flow by means of analogous particular solutions of the wave equation. Each such solution represents a concentrated
leap force. The elementary flow pattern in this case is restricted to the surfaces and interior of the Mach cone whose vertex lies at the point of application of the leap force. The lines indicating the direction of flow in a plane normal to the main flow direction are also shown in the figure below. It is seen that a large distance behind a wind flow in the neighborhood of the axis is identical to that produced by subsonic partial vortex.
Today, I'm going to discuss to you about the transonic problem. So, the main effects of the compressibility encountered in practical subsonic airplane designs are increase of drag, breakdown of lift, and as consequence of the second phenomenon, loss of control and maneuverability of wing-tail combinations. These effects are due to the breakdown of the continuous vortex free flow, rather than to the direct effect of compressibility of the air. The effects that occur before the breakdown have been analyzed by several methods. Ano nga ba ibig sabihin ito? Ang mga epekto nito ay dahil sa pagkasira ng tuloy-tuloy na vortex free flow. Sa halip na direktang epekto ng compressibility ng hangin, ang mga epekto na nangyayari bago ang pagkasira ay nasuri ng mga ilang pamamaraan. So ano ba yung vortex free flow? Ang free vortex flow is one in which the fluid mass rotates without any external impressed contact force. The whole fluid mass rotates either due to fluid pressure itself or the gravity or due to rotation previously imparted. The free vortex motion is also called potential vortex or irrotational vortex. So the first approximate theories of the compressibility effects were proposed by Brand and Glort using the assumption of small perturbations. The same assumption that was made in the supersonic case leading to the result given in this paper. In the subsonic case, it is possible to deduce a simple rule for the compressibility correction known as the Brand-Glort corrections, originally proposed by P. Molenbrock and A. Chaplygin and applied by several authors, especially to the problem of gas jets. By a modification of the original method of Chaplygin, H. S. Chen, and the authors made the method applicable to the problems of high-speed flow and especially useful for the calculation of forces acting on airfoils. The mathematical simplification is attained by replacing a portions of the adiabatic curve in the pressure versus volume diagram of the gas by a straight line. The Karman-Chen correction gave satisfactory results in a speed range in which the Brand-Glort corrections did not seem satisfactory. However, neither of the two methods can give a correct answers if the local velocity at the same point of the airfoil reaches the velocity. For this case, the theory must be reconsidered. It is the belief of the author that it will be difficult to find a simple unified method that remains valid in the speed of range with the flow of partially supersonic. It may be possible to find useful approximations for the pressure distributions by combination of typical subsonic and supersonic flow pattern. Extrapolations without safe theoretical foundations, however, although in the accord with the measurement in a few cases are bound to be inadequate of the experimental materials further extend. To continue the discussion, there are several doubtful aspects of the questions. First is, it has not been shown that the continuous solution composed of a supersonic and subsonic domain is the unique solutions. And the second one is, it has not been shown that this continuous solutions flow is a flow with the shock wave cannot exist below the theoretical critical Mach number. Certainly no such solution is possible before the velocity of the sound is reached locally. However, the behavior of the fluid between these two limits and has not yet been sufficiently explored theoretically, and the experimental evidence is also somewhat spotty. At the present state of knowledge, it seems to
appropriate to call the Mach number at which the local velocity reaches sound velocity. The lower critical Mach number and the Mach number beyond which no continuous flow is possible, that the upper critical Mach number is the condition gives unnecessary by conditions, visions, and the conditions of for the occurrence of the shock wave. The third one is, it can certainly be stated that the actual breakdown causing a rapid rise in drag and a drop in a lift must occur in the between lower and upper critical time limits. In no case has it been shown that the upper limit was attained experimentally. A major handicap in such investigations is the difficulty of finding the upper limit theoretically. Moreover, according to the classifications by H.S. Chen, the following factors may not be in the case of such large accelerations as necessarily occur near the upper critical limit. Alterations in the play of the dynamic forces, viscous stress due to the ordinary internal fluid frictions, viscous stress due to rapid compressions and expansions, relaxation lag in internal molecular vibrations, and the heart conductions. The author believes that especially instability of the continuous flow can lead to a premature appearance of shock waves. The experimental evidence, as also known as the boundary of layer, has considerable influence on the formation of shock waves. This problem is known as the interaction between boundary layer and the shock waves. It appears necessarily to devote at least a short discussion to this question. That's all. Thank you.
So moving on our topic, we will now be proceeding to wave drag. Wave drag is a force or drag that retards the forward movement of an airplane in both supersonic and transonic flight as a consequence of formation of shock waves. Wave drag is caused by formation of shock waves around the aircraft in supersonic flight or around some surfaces of the aircraft whilst in transonic flight. While in cruise, most civil jet aircraft fly in the Mach 0.75 or 0.85 range of speeds. Although shock waves are typically associated with supersonic aircraft due to their speed, they also form on an aircraft that travels less than the speed of sound on areas of the aircraft, such as the airfoils, where local airflow is accelerated to sonic speeds and then decelerated once again back to subsonic speeds. The shock wave forms at the point of the airflow becomes subsonic. As the aircraft continues to accelerate, the area of the wing experiencing supersonic flow increases. The shock waves move further back on the wings and becomes larger. Boundary layer separation also increases with the increase in speed, and if the speed is allowed to increase beyond the limiting Mach number or its MMO, severe buffeting, tuck or upset, loss of control may occur. Shock waves radiate a considerable amount of energy, resulting in drag on the aircraft. This drag can be reduced by incorporating one or more aerodynamic design features such as wing sweep with thin wings, fuselage shape, and anti-shock bodies and supercritical airfoils to accommodate its supersonic speeds. Next on the list is interference drag. It is a drag that is generated by the mixing of airflow streamlines between airframe components such as the wing and the fuselage, the engine pylon, and the wings, or in the case of a military or other special purpose built aircraft, between the airframe and attached external stores such as fuel tanks, weapon, sensor pods, or plane sponsons. This interference drag is generated when the airflow across one component of an aircraft is forced to mix with the airflow across an adjacent or proximal component. If one considers two parts of the aircraft that intersect at a particular point, such as the vertical and horizontal components of the empennage. It is obvious where the point of the intersection occurs. Each of these two components generate high velocity airflow across their respective surfaces. At the intersection of the two surfaces, there is less physical space for the airflow to occupy, resulting in a turbulent mixing of two different airflows and the production of a localized shockwave. Due to the shockwave, the resulting total drag from the empennage is greater than the sum of the drag produced individually by the vertical tail and horizontal tail surfaces. Other significant locations which generate interference drag include the wings or the fuselage junction and the wing and engine pylon or the fuselage engine pylon convergence. Interference drag can be minimized by the appropriate use of fairings and fillets to ease the transition between the components. Fairings and fillets use curved surfaces to soften the transition at the junction of the two aircraft components. This in turn allows the airflow streamlines to meet gradually rather than abruptly and reduces the amount of interference drag that is generated.
Interaction between boundary layer and shockwave. The concept of the boundary layer is based on the assumption that the flow conditions in the boundary layer, its growth or decrease, are fully determined by the velocity and pressure distribution of the non-viscous outside flow. In other words, one assumes that the flow outside of the boundary layer influences the development of the boundary layer, but there is no influence of the boundary layer on the main flow. In the case of an incompressible fluid or a compressible fluid moving at low velocity, it can be shown that this statement is really true unless the flow separates. The separation can be caused by a sharp corner or by a large magnitude of the so-called adverse pressure gradient. Unless there is a separation, the pressure across the boundary layer is sensibly constant and changes in thickness of the boundary layer do not influence the main flow appreciably. Fundamental assumption of the boundary layer theory cannot be applied to a flow in the transsonic speed range for two reasons. The first reason is the neighborhood of sonic velocity. A slight cross-section change causes large changes in pressure and velocity. It is known that in a flow through a supersonic nozzle, sonic velocity occurs at the minimum cross-section so that both slightly smaller or slightly larger velocities require a larger cross-section. This fact indicates that a flow near sonic velocity must be extremely sensitive to changes in cross-section. Therefore, if one considers the streamlined tubes passing just outside of the boundary layer, one must conclude that increase or decrease of the boundary layer thickness must have an essential influence on the flow in the neighborhood by narrowing or widening the cross sections of the neighboring streamlined tubes. Consequently, near the velocity of sound, there is an interaction between the main flow and the boundary layer in both directions. Second reason is since the flow in the boundary layer, at least near the wall, is certainly subsonic, no shock wave can extend through the whole boundary layer and end at the wall. Now, if the shock wave ends at some point inside of the boundary layer, the conditions that prevail must contradict the assumptions made in the boundary layer theory. The pressure discontinuity at the shock wave must create a steep pressure rise in the subsonic part of the boundary layer. The pressure across the boundary layer will no longer be constant, and therefore the ordinary boundary layer theory can hardly be applied. The large pressure rise may cause separation, and separation will, in general, react on the direction and magnitude of the shock wave. It has been known for a long time that in subsonic flow, critical changes in drag and stalling characteristics of airfoils depend on the relative location of the transition point between laminar and turbulent flow and the separation point. It is interesting to note that the same interplay between transition and separation also determines the formation of shock waves and therefore the drag and lift characteristics of airfoil sections and slender bodies at transonic speed. However, we are only at the beginning of understanding the phenomenon and have not yet reached the stage of practical conclusions.
She's a bad guy with ocean eyes. I think I love her. Party's over, not sober yet. It's my saddest summer. I need a favor. This bellyache got me hanging over. I say goodbye with the hope that maybe I gain some closure. Got no time to die. Can't live our lives in a movie. Not worth it.